Module 2, Joint Distributions, Probability Inequalities, and Theoretical Foundations. 1. Joint Distributions. So far in Module 1, we focused on the probability of a single random variable at a time. But in real life, variables often occur together and may influence one another. That's where joint distributions come in. A joint distribution tells us the probability of two or more random variables taking certain values at the same time. For example, the amount of rainfall in a month and the yield of a crop are related. More rain may lead to higher yields up to a point. The height and weight of people are correlated. Taller individuals often weigh more. Joint distributions allow us to answer questions like: what is the chance that it both rains more than 100 millimeters and the crop yield exceeds 3 tons per hectare? What is the probability that a person is between 170 and 180 centimeters tall and weighs between 70 and 80 kilograms? Marginal and conditional distributions. From a joint distribution, we can zoom in to look at just one variable, ignoring the other. This is called a marginal distribution. It's like looking at a single column or row in a table of probabilities. We can also condition on one variable, meaning we fix one variable at a certain value and see how the probabilities of the other variable behave. This is called a conditional distribution. These tools are powerful for exploring relationships and dependencies between variables. Independence. If two variables are independent, knowing the value of one tells you nothing about the other. For example, the outcome of a fair coin toss and the color of the next car that drives by are independent events. However, in real-world data, true independence is rare. Most phenomena are influenced by overlapping factors. 2. Chebyshev's inequality. Now let's discuss a general probability inequality called Chebyshev's inequality. It gives us a way to bound the probability that a random variable will be far away from its average value. What's interesting is that Chebyshev's inequality works for any probability distribution, as long as we know the average and the spread. In simple terms, it says, no matter what the shape of the distribution is, most of the values will be reasonably close to the mean, and the fraction that are very far away can't be too large. This is reassuring in situations where we don't know much about the distribution. It still lets us say something about the concentration of values around the mean. 3. The law of large numbers. The law of large numbers is one of the most important results in probability theory, and it's surprisingly intuitive. It says that if you repeat an experiment over and over, and average the results, the average will tend to get closer and closer to the expected value. For example, flip a fair coin many times, and the proportion of heads will get closer to 50% as the number of flips increases. Measure the daily temperature over many years, and the average will settle near the long-term climate average. There are two versions of the law. Weak law, the average will be close to the expected value most of the time, given enough repetitions. Strong law, the average will eventually stay close to the expected value and not wander away. This law is the reason why large samples give more reliable estimates than small samples. 4. The central limit theorem. If the law of large numbers tells us that averages settle down, the central limit theorem tells us what the shape of that settling looks like. It says that when you take many independent observations from any distribution, with some reasonable conditions, and you average them, the distribution of those averages tends to look like a normal bell curve, even if the original data was not normally distributed. For example, the distribution of the sum of dice rolls tends toward a bell shape as you roll more dice. The distribution of average exam scores across many classes will tend to be bell-shaped, even if individual scores are skewed. This is why the normal distribution shows up everywhere. It's a natural consequence of averaging many small, random influences. 5. Summary of the two modules. At this point, we've covered: in Module 1, the foundations of probability, the meaning of random variables, and a tour of important probability distributions, uniform, exponential, normal, gamma, and beta, as well as conditional probability and Bayes' theorem. In Module 2, how to handle multiple variables at once through joint distributions, the general bound of Chebyshev's inequality, the stabilizing power of the law of large numbers, and the universal shape-giving effect of the central limit theorem. Together, these ideas form the backbone of probability theory. They give us the tools to reason about uncertainty, model real-world randomness, and make informed predictions in science, engineering, business, and everyday life.